It seems like one of the few questions in astronomy with an easy answer. The universe is about 13.8 billion years old. Light travels at a fixed speed, so the farthest we could ever see must sit 13.8 billion light years away. It feels airtight. But that simple sum is wrong, and not by a little. The true distance to the edge of what we can see is about 46.5 billion light years in every direction, a sphere 93 billion light years across, sitting inside a universe far too young to allow it. Most of the galaxies you can see tonight are racing away from you faster than light. The oldest light of all, once a fierce glow, now arrives stretched into a cold whisper barely 2.7 degrees above absolute zero. And the whole sphere is still swelling, year after year, even as it quietly carries most of itself beyond your reach forever. So how big is the universe really, and why won't its edge hold still? Get comfortable. Hit subscribe if you're new here, because by the end of this, the night sky will feel far larger and far stranger than that simple arithmetic ever let on. Now, let's slowly ease into this. Part 1. The answer that feels obvious. There is a number almost everyone carries quietly in the back of their mind, and it feels like one of the few solid facts about the universe. The universe is about 13.8 billion years old. You have heard it so many times that it has stopped sounding strange, and from that single number, it seems you can work out something even grander. If the universe began 13.8 billion years ago, and if nothing in it can travel faster than light, then the farthest we could ever possibly see is 13.8 billion light years away. Light has had exactly that long to travel, and not a moment more. Draw a sphere of that radius around the Earth, and there, it seems, is the edge of everything we are allowed to know. It is a clean and satisfying piece of reasoning. It uses only two facts, both of them true, and it arrives at a tidy answer with no loose ends. The age of the universe sets the time, the speed of light sets the pace, and multiplying one by the other gives the reach. Most people who have thought about the size of the observable universe have followed exactly this path and felt, reasonably, that they understood the shape of the cosmos. A bubble 13.8 billion light years across, with us somewhere inside it, and a wall of darkness at the far rim where the light simply has not had time to arrive. Tonight, though, we are going to take that comfortable answer apart, slowly and gently, and put something far stranger in its place. Because that number, as reasonable as it sounds, is wrong. Not slightly wrong, not wrong at the edges, but wrong by more than a factor of 3. The true radius of the part of the universe we can see is not 13.8 billion light years. It is closer to 46.5 billion light years, in every direction you care to look. The whole sphere stretches something like 93 billion light years from one side to the other, and that is only the part we can observe. The actual universe is larger still, perhaps without any limit at all. If you are sitting with that for the first time, the obvious reaction is that something has gone badly wrong with the bookkeeping. How can we possibly see something 46 billion light years away if the universe has only existed for 13.8 billion years? Light from that object would need 46 billion years to reach us, and the universe has not lasted nearly that long. The light should still be in transit. It should not be here yet. And yet here it is, arriving in our telescopes night after night, carrying images of galaxies whose present distance is far greater than any straightforward reading of the speed of light should allow. This is not a trick of definitions, and it is not a rounding error in some cosmologist's spreadsheet. It is a real feature of the universe we live in, and understanding it will quietly rearrange the way you picture everything above your head. By the time we are finished, the night sky is going to feel less like a fixed ceiling with a wall at the back of it, and more like a surface that is breathing slowly outward, swelling year after year, as ancient light keeps washing in from places that should be impossibly far away. For now, let us simply sit with the size of the disagreement, because the size is the whole point. The intuitive answer and the real answer are not close. They are separated by more than 30 billion light-years of radius, which is to say by a gulf so enormous that no small correction could ever close it. Something fundamental about the way distance works in an expanding universe has to be different from the way distance works inside a room, or inside a solar system, or anywhere our intuition was trained. And the difference is not subtle once you see it. It is the difference between a universe that sits still while light crosses it, and a universe that grows underneath the light as it travels. It is worth remembering that this is not an old idea, and that for most of human history, even the greatest thinkers assumed the universe was fixed and unchanging in size. The notion that space itself could grow only arrived in the 1920s, when the astronomer Edwin Hubble, building on the careful work of others, found that distant galaxies were almost all moving away from us, and that the farther away a galaxy sat, the faster it was receding. That simple pattern, more distance meaning more speed, is exactly what you would expect if the space between everything was stretching uniformly, and it was the first hard evidence that the cosmos was not a finished room, but an unfinished and expanding one. Even Albert Einstein had at first assumed a static universe, and had inserted a term into his own equations to hold it still, a choice he is said to have later regretted. Once you accept that the universe has been expanding for its entire history, the question of its size stops being a matter of simple multiplication and becomes a question about that history itself. How fast was space stretching long ago, and how fast is it stretching now, and how has that rate changed over billions of years? Those questions turn out to have surprising answers, and the answers are what set the true scale of everything we can see. The comfortable sum we started with quietly assumed the rate of expansion was zero, that space did nothing at all while light crossed it. The real universe has never, for a single instant, held that still. To feel why this matters, picture the simplest version of the wrong idea. Imagine the universe as an enormous but motionless hall. At one end, 13.8 billion years ago, a lamp switches on. Its light sets off across the hall toward you at a fixed speed, and you count the years until it arrives. In a hall that never changes shape, the distance the light covers is exactly the distance to the lamp, and the time it took, multiplied by the speed of light, gives you that distance precisely. In that frozen hall, the intuitive answer is the right answer. The farthest lamp you could see would indeed be 13.8 billion light-years away, no more. But our universe is not a motionless hall. The floor of it has been stretching the entire time the light has been crossing, and stretching everywhere at once, so that the lamp and the wall and every point in between have all been carried farther apart during the journey. The light kept moving at its fixed speed, faithfully, the whole way. The ground it was moving across did not hold still. And when ground stretches beneath a traveller who is moving at a fixed pace, that traveller ends up far, far farther from home than their walking speed alone would suggest, because home itself kept receding while they walked. That single idea, the stretching of space during the journey of light, is the key that unlocks the entire puzzle of the title. It is why the observable universe is so much larger than its age seems to permit. It is why that size is not even a fixed thing, but a number that keeps climbing. And it is why, at the very end of this story, we are going to run into something genuinely unsettling, which is that the same stretching that makes the visible universe grow is also, at this very moment, carrying most of it permanently out of our reach. We are going to build this carefully, one layer at a time, because every layer overturns the one beneath it. We will start by pinning down what we actually mean by the size of the observable universe, since, as you will see, there is no single honest answer to that question, but three different ones that disagree with each other by enormous margins. We will find the wall at the edge of sight and discover that it is not a wall at all, but the oldest light in existence, stretched almost beyond recognition. We will watch galaxies that are racing away from us faster than light, which sounds impossible and is not. And then we will come to the strange double truth at the heart of all of it, that the universe we can see is getting larger, while the universe we can ever touch is getting smaller, and that both of those changes are happening because of the same quiet, relentless expansion. None of this requires you to abandon the two facts you started with. The universe really is about 13.8 billion years old. Light really does travel at a fixed and unbreakable speed through space. Those are not the mistakes. The mistake is a hidden third assumption that slipped in without anyone announcing it. The assumption that the distance between 2 points stays the same while light crosses between them. Remove that one quiet assumption, and the comfortable bubble 13.8 billion light-years across dissolves, and a far grander structure takes its place. So hold the simple answer in your mind for just a moment longer, the way you would hold something you are about to set down for good. 13.8 billion years old, 13.8 billion light-years to the edge, a tidy sphere with a dark wall at the rim. It is the picture almost everyone has, and it is the picture we are about to leave behind. Because the moment you ask how far away the most distant galaxies actually are right now, today, as you are listening, the tidy sphere comes apart in your hands, and the number that replaces it is one that should not fit inside the age of the universe at all. Let us go and find out exactly how big it really is, and why no measuring tape made for a room will ever give you the right answer out here. Part 2. The number that refuses to fit. Let us put the real number on the table and look at it directly, because it is worth seeing in full before we explain it. The matter whose light is arriving at our telescopes from the most distant reaches of the sky is, as of tonight, about 46.5 billion light-years away from us. Not where it was when the light set out, but where it is now, carried there by the expansion of space during the journey. That distance, measured in every direction, makes the observable universe a sphere roughly 93 billion light-years across. Astronomers usually quote it in their own units as about 28.5 gigaparsecs, but the light-year version is the one that lands because you can hold it against the age of the universe and feel the contradiction. The contradiction is sharp. The universe is 13.8 billion years old, and we are claiming to see things that are now 46 billion light-years away. The two numbers do not merely fail to match, they fail to match by more than a factor of 3, and that mismatch is not a flaw in the measurement. It is one of the most carefully checked results in all of science. We did not guess it. We measured it, using the only honest tool the universe gives us for gauging cosmic distance, which is not a ruler and not a radar pulse, but the stretching of light itself. This is the first place our everyday intuition has to be set down. When you want to know how far away something is in ordinary life, you can pace it out, or bounce a signal off it and time the return, or compare its apparent size to its known size. None of those methods works across billions of light years. We cannot pace out the cosmos. We cannot wait for a radar echo that would take 90 billion years to return. What we can do is catch the light an object sends us and ask a single, precise question of it. How much has your wavelength been stretched on the way here? That stretch is called redshift, and it is the bedrock measurement of cosmology. Everything we say about the scale of the universe is built on it. The reason redshift is so powerful is that the stretching of light is not separate from the expansion of space. They are the same thing. As space expands during light's long flight, the wave riding through that space is stretched along with it, drawn out toward longer, redder wavelengths. A wave that left a young galaxy as ordinary visible light can arrive at our instruments, shifted all the way into the infrared, because the space it crossed grew while it traveled. Measure how much the wave has been stretched, and you have measured how much the universe has expanded since the light began its journey. From that, knowing how expansion has behaved over cosmic history, you can work out both how long the light has been traveling and how far away its source has been carried in the meantime. When you run that calculation for the most distant galaxies, the answer comes out exactly as strange as the title promises. A galaxy whose light has been traveling for, say, 13 billion years did not sit 13 billion light-years away and wait. It has been swept outward the entire time, so that its present distance is far greater than the distance the light covered. The light travel time and the current distance have come unhitched from each other, and the gap between them is enormous. This is not a fudge introduced to save a theory. It is what the redshift measurements directly require, and the same framework that produces these distances also predicts, correctly, the brightness of distant exploding stars, the precise pattern of ripples in the early universe, and the temperature of the faint radiation that fills all of space. There is something almost vertiginous in realizing that the deepest images we have are not images of where anything is. They are images of where things were, long ago, with the where they are now smuggled in only as a calculation. When you look at a photograph of a galaxy near the edge of the observable universe, you are looking at light that left it when the cosmos was an infant, perhaps less than 1 billion years old. The galaxy in that picture does not look like that anymore, and it is not where the picture seems to place it. It has aged for billions of years and been carried billions of light-years onward. The image is a portrait of the past, dressed up as a snapshot of the present, and the universe never tells you this unless you know to ask. The history of how we learned to read that stretched light is worth a moment, because it shows how recent and hard-won this understanding is. In the years around 1912, the astronomer Vesto Slipher began measuring the light of distant spiral nebulae, objects later understood to be entire galaxies, and found their light systematically shifted toward the red. He did not yet know what it meant. It took the rest of that decade and the work of others to recognize the pattern that nearly everything was receding, and that the recession grew with distance in a steady proportion. From that proportion came the first crude estimates of how fast the universe was expanding, and therefore the first hints that distance and travel time had come apart. The confirmation that this framework is correct, and not merely a convenient story, comes from places far removed from the original galaxy measurements. When a particular kind of exploding star, bright and predictable enough to serve as a distance marker, is observed across billions of light-years, its brightness and its redshift agree precisely with what an expanding universe predicts, and with nothing else. When the faint patterns in the oldest light are mapped in fine detail, they too match the expanding picture to remarkable accuracy. And when astronomers watch the light of distant supernovae stretched out not only in colour but in time, so that the explosions appear to unfold in slow motion, they find exactly the slowdown that expanding space requires. 3 independent lines of evidence, built from entirely different physics, all point to the same conclusion, and the impossible-seeming size of the universe is the honest output of measurements checked from every direction we know how to check them. Now, you might reasonably wonder how solid that 46 billion light-year figure really is, given how counterintuitive it sounds. The honest answer is that the precise value depends on a number that scientists are currently arguing about, and that argument is itself one of the most interesting unsolved problems in physics. The size of the observable universe is tied directly to how fast the universe is expanding, a quantity called the Hubble constant. And right now, there are 2 respected ways of measuring that expansion rate, and they disagree. One method reads the expansion rate from the faint radiation left over from the early universe, and it lands near 67 kilometers per second for every megaparsec of distance. The other method builds a ladder of distances out through the nearby universe, using exploding stars and pulsing stars as mileposts, and it lands closer to 73. Those two numbers should be identical because there is only one universe with one expansion rate. Instead, they sit stubbornly about 9% apart, and the gap has refused to close, even as both measurements have grown more precise. Scientists call this the Hubble tension, and it has reached the point where the disagreement is far too large to be written off as bad luck. Either one of these excellent measurements hides an error no one has found, or the standard story of the universe is missing a piece. That uncertainty wobbles the exact size of the observable universe by a small amount. But notice what it does not do. It does not rescue the comfortable old answer. Whether the radius is 45 billion light-years or 48, it is still more than 3 times larger than the age of the universe allows under the frozen Hall picture. The tension changes the last digits. It does not touch the central fact. The observable universe is far, far bigger than 13.8 billion light-years, and it is bigger for a reason that has nothing to do with how precisely we know the expansion rate, and everything to do with the fact that the universe expands at all. So we are left holding a number that, on its face, breaks the rule we started with. Nothing outruns light, and yet here is light from objects now 46 billion light-years away, arriving comfortably within a 13 billion-year-old cosmos. The resolution is not that the rule is broken. The resolution is that we have been quietly misunderstanding what the rule governs. The speed of light is a strict limit on how fast anything can move through space. It says nothing at all about how fast space itself can grow. And once you let space grow, distances start behaving in ways that no measuring tape built for a room could ever capture. That is the door we are about to walk through. In the next part, we are going to stop treating space as the fixed stage on which the universe performs, and start treating it as something that is itself part of the performance, something that stretches and swells and carries the galaxies along with it. Get comfortable, because this is the idea that everything else rests on. Once you truly see that space is not a backdrop, but a participant, the impossible size of the universe stops being a paradox and becomes the only thing that makes sense. And it sets up the even stranger discovery waiting for us after that, the discovery that some of those distant galaxies are moving away from us faster than light, without breaking a single law of physics. Part 3. Space was never the stage. For almost all of human history, space was simply the container. It was the empty stage on which the real action happened, the nothing in which the something sat. Stars moved through it. Planets orbited within it. Light crossed it. But space itself was assumed to be inert, a fixed and featureless backdrop that did not participate. This is such a natural way to think that it barely feels like an assumption at all. The room you are in is not growing. The distance to the far wall is the distance to the far wall. Why would the universe be any different? The answer, worked out over the last 100 years and confirmed many times over, is that the universe is profoundly different, and that space is not a backdrop at all. Space is a participant. It stretches. The distance between 2 points that are not held together by gravity or by any other force does not stay fixed, but grows with time, everywhere, all at once. This is not the galaxies flying apart through a static space like fragments from an explosion. It is the space between the galaxies lengthening, swelling, so that things drift apart, not because they are moving, but because the ruler between them is getting longer. The classic way to feel this is to imagine an ant walking along a rubber band. Set the ant at one end and let it crawl toward the other at a steady, modest pace. In an ordinary world, it covers the band in a predictable time. But now, imagine that as the ant walks, someone is stretching the rubber band, lengthening it continuously beneath the ant's feet. The ant never speeds up. It always crawls at the same modest pace relative to the rubber directly under it. And yet the far end keeps retreating, because the band between the ant and its goal keeps growing. The ant's journey takes far longer and covers far more total length than its walking speed alone would ever suggest. When it finally arrives, the distance it has traveled bears no simple relationship to how fast it was walking, because the ground itself was being manufactured beneath it the whole way. Light crossing the expanding universe is that ant. It moves at its fixed and unchanging speed relative to the space immediately around it, always, without exception. But the space between a distant galaxy and the Earth has been stretching for billions of years, lengthening beneath the light as it travels. So, the light arrives having crossed far more total distance than its speed and its travel time would imply, and the galaxy that emitted it has been carried by that same stretching to a present distance enormously greater than where it sat when the light departed. This is the whole resolution of the paradox. The light has been travelling for 13 billion years, but the galaxy is now 46 billion light-years away because the rubber band of space did not hold still. This distinction has a pair of names worth keeping straight, because the confusion between them is exactly the confusion that makes the universe seem paradoxical. The distance the light actually covered, the path it physically traced, is the light travel distance, and for the oldest light, it is roughly 13.8 billion light-years, which is just the speed of light multiplied by the travel time. The distance to where the source sits right now, after all that stretching, is the proper distance, and for the same oldest light, it is the 46.5 billion light-years we have been circling. They describe the same object. They are simply answering two different questions. How far did the light go, and how far away is the sender today? In a static universe, those two questions have the same answer. In our universe, they come apart, and the gap between them is the fingerprint of expansion. Notice that none of this requires anything to move through space faster than light. The light itself never broke the speed limit. Every galaxy, measured against the space right beside it, is sitting more or less still, drifting only slowly. What grew was the space in between, and space is under no obligation to obey the speed limit that governs motion through it. The cosmic speed limit is a rule about how fast you can travel relative to your local surroundings. It is not a rule about how fast the distance between two far-apart surroundings can increase, because that increase is not anyone travelling anywhere. It is the stage itself lengthening, and the stage was never asked to stay within the speed limit of the actors on it. This is the single idea that the entire title rests on, so it is worth letting it settle rather than rushing past it. The universe is not a fixed hall with light crossing a frozen floor. It is a swelling volume in which every unbound distance is quietly growing, and light threads its way across that growth at a constant local pace while the destinations keep sliding away. The size of the observable universe is enormous compared to its age, precisely because the floor has been manufacturing new distance the entire time. The expansion is not violent, and it is not local. You do not feel it, the Earth does not feel it, the solar system does not feel it, because gravity binds those things together far too tightly for the gentle stretch to matter. It is only across the immense unbound gulfs between galaxies that the stretching accumulates into something staggering. There is a second image that helps as much as the ant on the rubber band, and it is worth keeping both in mind, because together they close off the wrong intuition from two sides. Picture a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin, and a raisin sitting anywhere in the loaf would see all its neighbours receding, the nearer ones slowly and the farther ones faster, in exact proportion to their distance. No raisin is at the centre of the rising. There is no centre. The dough is simply growing everywhere at once, carrying the raisins apart without any of them swimming through the dough at all. Our galaxies are the raisins, and the space between them is the dough, and the recession we measure is the rising, not the swimming. The reason this matters so much is that it dismantles the most stubborn version of the wrong picture, the one in which the Big Bang was an explosion at a particular point in space, flinging matter outward into a pre-existing emptiness. That is not what happened, and holding on to it quietly poisons every later attempt to understand cosmic scale. The expansion did not begin somewhere and spread outward. It began everywhere, all at once, in all the space there was, and it has been happening everywhere ever since. There is no point you could travel to and say, here is where it started, here is the center from which everything flew. Every location, including the one you occupy right now, has equal claim to being the place the expansion is happening, because the answer is that it is happening at all of them. That single correction, expansion as a property of all space rather than an explosion from one spot, is the thing that makes the rest of this story coherent rather than baffling. And accumulate it does. Over a single year, the stretch added to the space between two nearby galaxies is utterly negligible. Over billions of years, across billions of light years, those negligible stretches pile up without end until the total distance added dwarfs the distance the light first set out to cross. The far reaches of the observable universe are far, not because anything raced out there, but because the patient, ceaseless lengthening of space had billions of years to work and billions of light years to work across. Time and scale turn a gentle stretch into a gulf that light, for all its speed, can barely keep pace with. Once you hold this picture, a great many cosmic puzzles stop being puzzles. The impossible size of the universe becomes natural. The arrival of light from objects now far beyond any light travel reach becomes expected. And a new question quietly opens up beneath your feet, which is what we even mean by distance when the thing we are measuring keeps changing length while we measure it. If the proper distance to a galaxy is growing every second, then the moment you state it, it is already out of date. There is no single fixed number that captures how far away anything truly is, because far away is a moving target in an expanding universe. This is where the comfortable idea of a single size for the observable universe finally breaks down completely. We have already met two different distances to the same oldest light, the light travel distance of about 13.8 billion light-years and the proper distance of about 46.5 billion. In the next part, we are going to meet a third way of describing that same edge, one that does not pretend to be a distance at all, but reports instead how much the light has been stretched. And we are going to find that this third description, the redshift, is in some ways the most honest of them all, because it is the only one we actually measure rather than calculate. 3 different answers to the question, how big is the observable universe? All of them correct, all of them describing the same sphere of sky. The reason they can all be correct at once is the reason we are about to explore, and it will change what the word distance even means to you when you look up. Part 4. What distance even means out here? We have already collected 2 different distances to the same edge of the universe, and it is worth pausing to admit how unusual that is. In ordinary life, an object has one distance. The far wall is across the room, and there is a single honest number for how far across. But the most distant light in the sky can be truthfully described as 13.8 billion light-years away in the sense of how far the light travelled, and as 46.5 billion light-years away in the sense of where the source sits now. Both numbers are correct. They are simply answers to different questions, and the universe refuses to collapse them into one. To really understand the scale of what we can see, we have to make peace with the fact that distance, out here, is not a single thing. There is a third way of describing that edge, and in some ways it is the most truthful of all, because it is the only one we actually observe rather than infer. That third description is the redshift, the raw measurement of how much the light has been stretched on its way to us. For the most distant galaxies confirmed so far, the light has been stretched by a factor of 15 or so, meaning every wave arrived more than 15 times longer than it left. For the oldest light in the universe, which we will meet properly in a moment, The stretch is a factor of about 1100. The redshift does not pretend to be a tidy distance in light years. It reports something more direct, which is how much the universe has grown since the light began its journey. A redshift of 1100 means space has expanded roughly 1100-fold since that light set out. What makes the redshift the honest measure is that everything else is a calculation built on top of it. We measure the stretch. From the stretch, using our best understanding of how expansion has changed over cosmic time, we work out a travel time and a present distance. The light travel distance and the proper distance are both derived. The redshift is observed. This is why, when astronomers describe the farthest objects, they so often give a redshift rather than a distance in light years. The redshift is what the telescope actually saw. The distances are interpretations of it, and interpretations can shift as our understanding of the expansion improves. The stretched light is the fact. To make all of this manageable, cosmologists lean on a fourth idea, a kind of distance that deliberately strips the expansion back out. Imagine laying down a grid across the universe that expands along with it, so that each galaxy keeps the same grid coordinates forever, even as the real distances between the grid lines grow. A galaxy that sits at a certain coordinate today sat at that same coordinate billions of years ago, and will sit there billions of years from now, because the grid stretches in lockstep with space. The distance measured on that co-expanding grid is called the comoving distance, and its great virtue is that it stays fixed while the universe grows. The co-moving distance to the edge of the observable universe is, by design, set equal to today's proper distance, that same 46.5 billion light-years. It is the bookkeeper's distance, the one that holds still so the accounting stays sane. To see why cosmologists bother with such a peculiar invention, think about what happens if you try to do without it. Suppose you want to say where a particular distant galaxy is, and you insist on using ordinary present-day distances. The trouble is that the present-day distance to that galaxy is changing every second, growing as space expands, so any number you write down is stale the instant you write it. State that a galaxy is 30 billion light-years away today, and tomorrow it is farther, and a century from now farther still, with no fixed value to anchor to. The co-moving distance solves this by riding along with the expansion, so that the galaxy keeps the same co-moving coordinate forever, even as the real gap between us grows. It is a way of labeling positions in a universe where the actual distances refuse to sit still, and almost every map a cosmologist draws of the large-scale cosmos is drawn in these co-expanding coordinates for exactly that reason. What this machinery reveals, once you have it, is that the 3 or 4 different distances are not competing answers, but different and equally valid descriptions of one situation. The light travel distance tells you about the journey. The proper distance tells you about the present gap. The co-moving distance gives you a stable label that does not drift, and the redshift is the raw observation underneath them all. Asking which one is the real size of the observable universe is a little like asking whether the real description of a journey is its duration, its present distance from home, or the fuel it consumed. Each is true. Each answers a different question, and the confusion only arises when you expect a single number to do all of their jobs at once. The universe, out at these scales, simply does not offer one number that does everything, and learning to be comfortable with that is most of what it takes to understand cosmic distance. Why does any of this bookkeeping matter to you, listening tonight? It matters because it dissolves the last trace of the paradox we started with. The reason a 13 billion-year-old universe can be 93 billion light-years across is that there is no single quantity called the size of the universe doing impossible work. There is the distance the light travelled, which is modest and obeys every intuition. There is the distance to the source now, which is enormous because space has been stretching the whole time. And there is the stretch itself, the redshift, which is simply the honest record of how much growth has happened. None of these three breaks any law. They only break the assumption that distance is one fixed thing, and that assumption was never a law to begin with. There is a quieter consequence hiding in here, one that will return at the very end of our story with far more weight than it carries now. Because the universe looks essentially the same in every direction, and because every observer measures these same kinds of distances around themselves, each observer naturally finds that they sit at the center of their own observable sphere. You are at the center of yours. 46 billion light-years of universe surrounds you on every side, and you are precisely in the middle of it. So is a being on a world in one of those distant galaxies who looks out and finds their own sphere, with you somewhere near its faint and ancient edge. Everyone is at the center. You are standing at the center of a sphere that has no center, and we will come back to that sentence when you are ready to feel the full strangeness of it. For now, hold it lightly. It is enough to notice that the centeredness you would feel if you could survey the whole observable universe is not a sign that you occupy a special place. It is exactly what an expanding universe with no center produces for everyone inside it. The observable universe is not a region of space marked off by walls. It is a region marked off by you, by where you happen to stand and when you happen to live. Move to another galaxy, and your observable universe moves with you, a new sphere centered on the new location, overlapping the old one but not identical to it. The edge is not painted onto the cosmos. It is cast by the observer, like the horizon at sea, which belongs to the sailor and not to the ocean. That comparison to the horizon at sea is going to do a lot of work for us before the end, so let us name it clearly. When you stand on a ship and look out, there is a circle beyond which you cannot see, not because the ocean stops there, but because the curve of the earth and the height of your eye conspire to hide what lies past it. Sail toward that circle, and it retreats. Another sailor, miles away, has their own circle centered on them. The horizon is real. It genuinely limits what you can see, and yet it is not a thing out in the water. It is a relationship between you and the world. The edge of the observable universe is a horizon in exactly this sense, a limit set by your position in time and the finite speed of light, and not a feature of space itself. We are now ready to go and find that edge, and to discover what it is actually made of. Because there really is something at the limit of our sight, a definite boundary beyond which our telescopes go dark, and it is not an arbitrary line where the light merely ran out of time. It is a surface, an oldest light, a glow that fills the entire sky in every direction and marks the moment the universe first became clear enough to see through. In the next part, we are going to travel out to that wall of light and ride a single ancient photon across the whole age of the cosmos to reach it. And when we arrive, we will understand why looking as far as it is possible to look is the same as looking as far back in time as it is possible to remember. Part 5. The Wall of Light. When you point the most powerful telescope ever built at a patch of seemingly empty sky and let it stare, you see galaxies, and behind them fainter galaxies, and behind those fainter still, each one further away and further back in time. You might expect this to continue without end, deeper and deeper, galaxy behind galaxy forever. It does not. At a certain point the galaxies stop, and beyond them there is a different kind of light entirely, a faint and uniform glow that fills every direction of the sky at once. This glow is the oldest light in the universe, and it is the true wall at the edge of sight. Astronomers call it the cosmic microwave background, and reaching it is the same as reaching the limit of what light can ever show us. To understand what this glow is, we have to go back to the universe, as it was a very long time ago, when it was young and hot, and entirely unlike the clear, dark space we know. For its first few 100,000 years, the universe was so hot that ordinary atoms could not hold together. Electrons were torn loose from nuclei and flew free. And a universe full of free electrons is opaque, because light cannot travel through it without being scattered almost immediately. Any photon trying to cross that early cosmos would have bounced from one charged particle to the next, like light trying to pass through a dense fog. The early universe glowed, but it was not transparent. It was a wall of luminous fog, and you could not see through it any more than you can see through the surface of the sun. Then, about 380,000 years after the beginning, the universe cooled enough for something decisive to happen. The temperature dropped to a few thousand degrees, cool enough that electrons could finally settle onto nuclei and stay there, forming the first stable neutral atoms. The moment the free electrons were swept up into atoms, the fog lifted. With nothing left to scatter it, light could suddenly stream freely across space for the first time, and it has been streaming ever since. The light released in that instant, when the universe became clear, is the light we still see today as the cosmic microwave background. It is a snapshot of the entire sky. At the moment it first became transparent, the baby picture of the cosmos, preserved and still arriving. Now consider what that light has been through to reach us. It set out about 13.8 billion years ago, when the universe was a few thousand degrees and glowing a fierce orange-white. For all the time since, it has been crossing space that would not stop expanding, and every bit of that expansion has stretched it. By the time it arrives at our instruments, its waves have been pulled out by a factor of roughly 1100, dragged from a hot, visible glow all the way down through the infrared and into the microwaves, which is why we need radio dishes rather than eyes to detect it. Its temperature, once thousands of degrees, has been stretched down to a whisper, just 2.725 degrees above absolute zero. The fiercest light in the early universe reaches us as the faintest cold hiss imaginable, and that cooling is nothing but the expansion of space written onto the light. Picture riding one of those photons. You begin your existence in a sea of glowing plasma, hemmed in on every side, scattered so often you can barely move in a straight line. Then, in a single sweeping instant across the whole universe, the fog around you clears, the last charged particles vanish into neutral atoms, and the path ahead of you opens into darkness. You leap forward at the speed of light, and you do not stop. For 13.8 billion years you fly, and the entire way the space ahead of you keeps unrolling, stretching your wave longer and longer, draining your warmth degree by degree. The orange glow of your birth reddens, deepens, slides into the infrared, and finally into the long, slow waves of the microwave band. You cross the forming and dying of stars, the assembling of galaxies, the whole history of structure in the cosmos, never touching any of it, until at last you fall into a radio dish on a small blue world and register as a faint, cold tick, 2.7 degrees above the absolute floor of cold. You are the most travelled messenger in existence, and your message is a portrait of the universe as an infant. The discovery of this glow is one of the quietly great stories in science, and it happened almost by accident. In the middle of the 1960s, two researchers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna and kept finding a faint hiss of microwave noise that they could not get rid of, no matter which direction they pointed or how carefully they cleaned the equipment. They suspected everything, even the droppings of pigeons nesting in the antenna, before they understood what they had. The hiss was not a flaw. It was the cooled afterglow of the early universe, arriving from every direction at once, exactly as a handful of theorists had predicted it should. They had stumbled onto the oldest light in existence, and the find reshaped cosmology overnight. In the decades since, instruments built specifically to study that glow have measured it with extraordinary care, and what they found only deepened the wonder. The light is almost perfectly smooth across the whole sky, the same temperature in every direction to within a few parts in 100,000, which tells us the early universe was astonishingly uniform. But it is not perfectly smooth, and the tiny variations that do exist, regions a hair warmer or cooler than average, are the seeds from which every galaxy and cluster later grew. Written into that faint, cold, ancient light is both the uniformity of the infant cosmos and the first faint wrinkles that would become all the structure there is. The wall at the edge of sight is not blank. It is a detailed photograph of the beginning, and we are still reading the fine print in it. This is why the cosmic microwave background is the wall at the edge of our vision. It is not that the universe stops there. It is that we cannot see past the moment the fog lifted, because before that instant there was no free-flying light to carry an image to us. The microwave background is the surface of last scattering, the last place those photons bounced before the universe turned clear, and it forms an opaque curtain around us at the limit of sight. Look as far as you can in any direction, and you eventually hit it, this glow from every part of the sky at once, the oldest thing light can show you. Beyond it lies more universe, but it is hidden behind a wall of fog that no telescope can ever pierce with ordinary light. There is a profound idea folded into all of this, one that quietly reshapes what looking out even means. Because light takes time to cross space, every increase in distance is also an increase in how far back in time you are seeing. The sun you see is 8 minutes old. The nearest stars you see are years old. The nearest large galaxy you see is more than 2 million years old, its light having left before our species existed. And the most distant galaxies you see are billions of years old, shown to you as they were when the universe was young. You cannot look far without looking back. Distance and time are bound together so tightly that the edge of space is also the edge of memory, and the wall of light is simply the earliest moment the universe permits any image to escape from. This means there is a hard limit on observation that has nothing to do with the power of our instruments. We could build a telescope 1,000 times finer than anything we have, and it would still slam into the same wall of light at 380,000 years after the beginning, because before that the universe was opaque to light. There may be other messengers that can carry information from earlier still. Ghostly particles, called neutrinos, decoupled from the early universe when it was barely a second old, and ripples in space itself, primordial gravitational waves, could in principle carry an image from earlier yet. But those signals are so faint that we have not yet learned to read them clearly. For now, the wall of light stands, the oldest thing we can see, the boundary of the visible past. So we have reached the edge and found it is not an emptiness where the light ran out, but a luminous surface where the universe first became clear. And yet we have not explained the strangest part of the title at all. We have found how big the observable universe is and what marks its rim, but we have not yet faced the fact that some of the galaxies inside that rim, galaxies we can plainly see, are receding from us faster than light itself. That sounds like a flat contradiction of everything physics is supposed to allow. In the next part, we are going to walk straight into that apparent impossibility and discover that it is not impossible at all, and that understanding it is the final piece we need before we can explain why this entire sphere of sky keeps growing larger year after year. Part 6. Faster than light and still in view. Here is a fact that sounds, at first, like it has to be a mistake. A great many of the galaxies we can see right now, ordinary galaxies whose light sits in our telescopes tonight, are moving away from us faster than the speed of light, not close to it, faster than it. And this is not a fringe claim or a misreading of the data. It is a plain consequence of the expanding universe, accepted without controversy by every cosmologist, and it does not break a single law of physics. To see why, we have to return to the one idea that has carried us this far, the difference between moving through space and the stretching of space itself. Recall the rule the speed of light actually sets. Nothing can move through space, past its local surroundings, faster than light. A spaceship cannot outrun a beam. A particle cannot overtake a photon in a race through the same patch of space. That rule is ironclad, and nothing we are about to say violates it. But the recession of distant galaxies is not motion through space. The galaxies are sitting more or less still relative to the space around them. What carries them away from us is the lengthening of all the space in between, and that lengthening is not a speed of travel. It is the rate at which new distance is being manufactured across an immense gulf, and there is no law capping how fast distance can grow. The way the recession works is almost arithmetic in its simplicity. Every stretch of space between us and a distant galaxy is expanding a little. A galaxy twice as far away has twice as much space in between, and therefore twice as much total stretching, and therefore recedes twice as fast. 3 times as far, 3 times as fast. Keep going outward, adding more and more intervening space, and the recession speed climbs without limit. At some particular distance, the total stretching of all that intervening space adds up to a recession rate equal to the speed of light. And beyond that distance, the recession rate exceeds the speed of light, simply because there is even more space in between, each piece contributing its share to a sum with no ceiling. That special distance where the recession reaches light speed has a name. It is called the Hubble radius, or the Hubble sphere, and it sits at roughly 14.5 billion light-years from us. Inside it, galaxies recede more slowly than light. Outside it, they recede faster. And here is the part that snaps the intuition in half. The edge of the observable universe, at 46 billion light-years, lies far outside the Hubble sphere, which means most of the galaxies we can see are beyond the distance where recession reaches light speed. Most of the universe we observe is, right now, racing away from us faster than light, and we see it anyway. How can we possibly see something that is receding faster than light? The resolution lives in the long history of the light's journey. The light we are receiving from those galaxies left them billions of years ago, when both the galaxy and the expansion were arranged differently than they are now. In some cases, the galaxy was closer when the light set out. In some cases, the light spent ages struggling almost in place, like a swimmer fighting a current, the expansion carrying it backward nearly as fast as it swam forward, until the regions it was crossing eventually slowed enough in their recession to let it gain ground and finally reach us. The photon's arrival is not evidence that the galaxy is slower than light today. It is evidence that, across the long and complicated history of the journey, the light found a path through the expanding space that eventually delivered it to our door. The galaxy can be superluminally receding now and still have gotten its ancient light to us. It is worth slowing down on that struggling photon, because it is one of the strangest and most beautiful details in all of cosmology. Imagine a beam of light that set out toward us from a galaxy already receding faster than light. At the moment it left, the space between us and it was being stretched so quickly that the light, though aimed directly at us and moving at its full and constant speed, was actually being carried farther away with every passing year. For a long stretch of its journey, this photon made negative progress, losing ground despite swimming toward us as fast as anything can. It was like a swimmer striking out for shore against a current flowing seaward faster than they can swim, drawn backward even as they pull forward with all their strength. By every appearance, that light should never have reached us at all. And yet some of it did, and the reason is subtle. The expansion of the universe has not held steady. In its earlier history, the expansion was decelerating, the stretching of space slowing down as gravity pulled against it. As the regions the photon was crossing slowed in their recession, the current eased, and the swimmer who had been losing ground began, at last, to gain it. The light that had been swept backward for ages finally started closing the distance, crossed into regions receding slower than light, and eventually completed its journey to our telescopes. The photons arriving from the most distant galaxies are survivors of exactly this kind of epoch, sources that were receding faster than light when they set out, light that lost ground for 1 billion years before the slackening current let it through. That such messages reach us at all is a quiet miracle of timing written into the changing pace of cosmic expansion. This is the moment to introduce a phrase that is going to matter enormously by the end of tonight, so let us state it plainly and let it sit. To see is not to touch. Seeing a galaxy means its old light has reached you. It says nothing about whether you could ever reach the galaxy, or send a signal to it, or have any effect on it whatsoever. Those are entirely separate questions, and in an expanding universe, their answers come apart. You can see things you can never reach. You can receive light from a galaxy that is, at this very moment, so far away and receding so fast that no message you sent today, traveling at the speed of light, would ever arrive. The image in your telescope is a letter from the past. It is not a thread you can follow back to its sender. For now, that gap between seeing and touching may feel like a technicality, an interesting wrinkle with no emotional weight. Hold on to it anyway, because when we reach the dark energy twist near the end of our story, this quiet phrase is going to turn into something close to grief. The universe lets us see far more than it will ever let us reach, and the distance between those two is not fixed. It is widening. But that is for later. For now, the point is simpler and almost joyful. The faster-than-light recession of distant galaxies is not a paradox and not a scandal. It is the natural behavior of an expanding universe, and we observe it calmly every night, light arriving from objects that have long since been carried beyond the speed of light by the swelling of space. Now we have every piece we need to explain the strangest claim in the title, the claim that the observable universe is not just enormous, but growing. We have seen that space stretches, carrying distant things away. We have seen that the edge of sight is a horizon cast by our position in time, not a wall in the cosmos. We have seen that light arrives from sources now far beyond light travel reach, and that recession faster than light is ordinary out here. Each of these facts has prepared us for the realization that the boundary of what we can see is not fixed in place. It moves. It moves outward year after year, and it moves for two distinct reasons, each one strange in its own right. In the next part, we will take up the first of those two reasons, the gentler and more intuitive one. Every year, light that has been travelling toward us for the entire age of the universe finally completes its journey and arrives, and that arrival reveals a thin new shell of sky that was, the day before, still beyond our reach. The universe is not handing us its image all at once. It is delivering it slowly, a fresh layer every moment, as the oldest light keeps washing in from sources whose news had simply not yet had time to cross the gulf. The sphere of what we can see is filling in from the outside, and it has not finished. Let us go and stand at that growing edge and watch a new shell of the cosmos switch on. Part 7. The shell that switches on. The observable universe has an edge, and that edge is not standing still. It is moving outward, and the first reason is the gentler of the two, the one you can almost feel your way into without any mathematics at all. It comes down to a simple truth about light and patience. Light takes time to arrive, and at any given moment there is light still on its way that has not yet reached us. Tomorrow, some of that light will finally arrive, and when it does, it will reveal things that, today, we cannot see. Think about what it means that the universe has a finite age. 13.8 billion years ago, everything switched on, and light began crossing space in every direction. The farthest light that can have reached us so far is light that has been travelling for that entire span, the full age of the cosmos. But the universe did not stop producing light after the first instant, and it did not stop sending it our way. There is light that left its source 13.8 billion years ago and arrives today. There is light that left at the same moment, but from very slightly farther away, and it has not arrived yet because it had a touch farther to go. Tomorrow, that slightly more distant light completes its journey. The day after, light from a hair farther still. The edge of what we can see creeps outward as the oldest light keeps finishing its crossing. This is the horizon breathing outward, and it is worth picturing literally. Stand at the boundary of the visible sphere as a patient watcher, someone who could perceive across cosmic stretches of time. Light that left a galaxy 13.8 billion years ago has been in flight for your entire existence, and tonight its leading edge finally reaches you. A thin shell of sky that was dark a moment ago quietly fills with the faint red smear of galaxies that were always there, sitting at their coordinates, but whose light had simply not yet had time to arrive. Nothing moved to reveal them. No galaxy switched on. Time merely caught up to a journey that was already underway. Tomorrow another shell, fainter and older still, fills in behind it. The visible universe is not a static photograph. It is an image developing from the outside in, gaining a new outer layer every moment as the oldest light keeps washing ashore. Linger in that shell for a moment, because there is a tenderness in it that is easy to miss. The galaxies in the newly arriving shell did nothing to announce themselves. They have been there all along, sitting at their coordinates for billions of years, shining steadily into a darkness that simply had not yet reached us. Their light has been crossing the gulf the entire time, patient and unhurried, and tonight the front of that light finally laps against our instruments. We did not earn the sight by building a better telescope. We earned it by waiting, by being here at the moment the journey happened to finish. The universe is not performing for us. It is delivering, on its own schedule, a backlog of news so old that the senders have long since changed beyond recognition. There is also a humbling scale buried in how slowly this particular engine works. The shells that switch on do so at a measured pace, set by the speed of light and the patience of the journey, and across a single human lifetime, the change to the boundary from arriving light alone is far too small to notice with any eye or instrument we have. This is not growth you could watch the way you watch a sunrise. It is growth you infer, the way you know a glacier moves even though it looks still, and yet it never stops. Every second, somewhere around the entire sphere of sight, light is completing a 13 billion year crossing and lighting a sliver of sky that was dark the instant before. The boundary advances grain by grain, faithfully, whether anyone is watching or not, a slow and ceaseless filling in of the deep past that has been underway since the first light was free to move, and will continue for as long as there is light still on its way. There is a tender quality to this, once you let it land. The universe is not showing you everything at once. It is showing you a little more each day, delivering the deep past in installments, as fast as light can carry it. Every night, the sky contains, in principle, a sliver more universe than it did the night before, a fresh ring of ancient galaxies whose news has finally crossed the gulf. We will never run out of arriving light in any human time span, because there is always more of it still in transit, always a more distant source whose photons are nearly here, but not quite. The boundary of sight advances steadily, patiently, fed by a backlog of light 13.8 billion years in the making. Now, if this were the only reason the observable universe grew, it would already be a lovely fact, but it would be a modest one. Light arriving on schedule, the visible edge creeping outward at a steady pace, the universe parceling out its image one shell at a time. This alone would mean the sphere of what we can see is slowly enlarging, and that the children of the far future would, in principle, have a slightly larger observable universe than we do, simply because more light would have had time to arrive. It is a real effect, and it is the intuitive half of the answer to why the observable universe keeps getting larger. Light keeps arriving, and arriving light is the same as a growing edge. But notice that this gentle picture still treats the distances as if they only grow because we are waiting for light to cross them. It has not yet folded in the other thing we know, the thing that has haunted this entire story, which is that the space itself is expanding the whole time. The shells of sky that switch on are not sitting at fixed distances waiting to be illuminated. They are being carried outward, even as their light comes in. And when you combine the arrival of ancient light with the relentless stretching of the space that light is crossing, the growth of the observable universe becomes far more dramatic than steady waiting could ever produce. The edge does not merely creep, it races. To set up that second reason properly, hold the two ideas side by side. On the one hand, light is always arriving, finishing journeys begun billions of years ago, lighting up new shells at the rim of sight. On the other hand, every one of those shells, and all the space between us and them, is being stretched larger at the same time. The first effect alone would grow the observable universe gently, at something like the pace light itself sets. The second effect, the expansion, supercharges it, pushing the present distance to that edge outward far faster than any light beam travels. The full answer to the title is the marriage of these two, and the second partner is the more startling by far. There is also a quiet reassurance hidden in the first reason, before we let the second one complicate everything. The fact that new light keeps arriving means the universe is, in a sense, generous with its past. It does not hide its history behind a single closed door. It keeps opening the door wider, letting more of the ancient cosmos into view, refusing to be fully seen all at once, but never fully concealing itself either. The most distant galaxies in our deepest images are sources whose light only recently completed an almost unimaginable crossing, and there are countless more whose light is nearly here, waiting in the last stretch of the journey, ready to join the visible sky in the cosmic moments to come. So we have the first engine of growth in hand, and it is real, and it is gentle. The observable universe expands because light keeps arriving, revealing shell after shell of the deep past as the backlog of ancient photons finishes crossing the gulf. But this is only half the story, and the smaller half. In the next part, we are going to add the expansion of space directly into the picture and watch the growth of the observable universe turn from a steady creep into something that genuinely strains the imagination, a boundary that sweeps outward at several times the speed of light. We are going to shrink the entire universe down small enough to hold in your hands, and then let it swell, so you can feel in your bones why the edge of everything we can see is not just moving, but moving faster than the light inside it could ever chase. Part 8. The sphere that will not stop swelling. The second reason the observable universe keeps getting larger is not gentle at all. It is the expansion of space, and once you let it into the picture, the growth of the visible sphere stops being a steady creep and becomes a sweep so fast that no beam of light inside the universe could keep up with it. To feel this properly, we are going to do something the mind can actually hold, which is to shrink the entire observable universe down until it fits between your hands, and then let it grow. Imagine cupping your palms around a sphere the size of a held breath, and inside it, the whole observable universe in miniature. 93 billion light-years compressed to the width of your hands. Every galaxy is a single grain of light, suspended in the volume, hundreds of billions of them, motes hanging in the clear space between your palms. Now let time run forward, and watch what happens. The grains begin to drift apart, all of them, in every direction at once. Not because any grain is swimming through the space around it, but because the space between every pair of grains is lengthening. The sphere swells between your hands, and as it swells, the grains near the surface race outward faster than the grains near the center, because there is more lengthening space stacked up between you and them. The surface of the sphere sweeps outward faster than any single mote of light could travel across the inside. There is no center to the motion. Every grain sees every other grain fleeing, and every grain considers itself perfectly still. That image is not a metaphor laid on top of the physics. It is the physics. The expansion of space means that the present distance to the edge of the observable universe grows for two compounding reasons at once. Light keeps arriving, as we saw, revealing new shells, and the space holding those shells keeps stretching, so the present distance to each shell balloons, even as its light comes in. When cosmologists add both effects together properly, they find that the boundary of the observable universe, measured as a present distance, recedes from us at something like 3 times the speed of light. The edge of everything we can see is sweeping outward faster than light, carried by the expansion of the space it bounds. This is the engine that makes the numbers in the title possible. It is why the radius is 46 billion light-years, and not the 13.8 that light travel alone would give. The boundary has been racing outward, supercharged by expansion, the entire history of the cosmos, and it is why the observable universe keeps getting larger in a way that dwarfs the gentle arrival of light. The visible sphere is not filling in at the sedate pace of a light beam. It is being inflated from within by the growth of space, its edge driven outward faster than the very light that defines it. It can help to separate two things that the word growth is quietly bundling together, because keeping them apart is what makes this make sense rather than melt into confusion. There is the boundary itself, the present distance to the farthest matter we can see, and that distance grows fast, swept outward by expansion at several times light speed. And then there is the question of whether genuinely new material, matter we never could have seen before, is crossing into view. Those are not the same question, and their answers point in different directions. The present distance to the edge climbs dramatically, but the amount of genuinely new universe entering our view is governed by something subtler, and in a universe like ours, it does not climb forever. This is the hinge on which the whole story is about to turn. For most of cosmic history, the picture was straightforwardly hopeful. The observable universe grew, the boundary swept outward, and more genuinely new regions of the cosmos came into view as the eons passed. A universe expanding, but gradually slowing under its own gravity, would have kept this up indefinitely, handing each generation of observers a larger and richer cosmos than the last, more galaxies entering the visible sphere without end. Had we lived in that universe, the title of tonight's story would have only a bright side. The observable universe keeps getting larger, full stop, forever, with more to see at every turn. But we do not live in that universe. Starting a few billion years ago, the expansion of space stopped slowing down and began to speed up. Some property of space itself, which we call dark energy for lack of a better name, is driving the expansion to accelerate, pushing the galaxies apart at an ever-increasing rate. And an accelerating expansion changes everything about the future of what we can see. It means the growth of the observable universe, the genuine entry of new regions into view, does not continue forever. It is slowing toward a limit. The boundary still sweeps outward. The present distance to the edge still climbs, but fewer and fewer truly new galaxies will ever cross into our view, and eventually none will. The door that has been opening wider for 13 billion years is, in the deepest sense, beginning to close. This is the twist the title has been hiding, and it is worth stating without softening it. The observable universe keeps getting larger. Yes, in the sense that the present distance to its edge keeps growing. But the universe we can ever actually reach, ever touch, ever affect, or be affected by, is not growing. It is shrinking. Dark energy is carrying galaxy after galaxy across a second, more final boundary, beyond which no signal we could ever send, even at the speed of light, will ever arrive. The visible sphere swells. the reachable sphere contracts, and the same accelerating expansion is responsible for both. The discovery that the expansion is accelerating is itself one of the great surprises of modern science, and it caught nearly everyone off guard. In the late 1990s, two competing teams of astronomers set out to measure how fast the expansion was slowing down. Everyone expected it to be slowing because gravity pulls all the matter in the universe together and should, over time, put the brakes on the cosmic stretching. The only question seemed to be how much. The teams measured distant exploding stars to gauge the expansion across cosmic history, and the answer came back inverted from all expectation. The expansion was not slowing. It had been speeding up for billions of years. The result was so unexpected that the researchers spent a long time looking for their own mistakes before they accepted it, and the discovery later earned the highest honors in physics. We still do not know what is driving that acceleration, which is why it carries the deliberately vague name of dark energy, a label that mostly marks the boundary of our ignorance. We can measure its effects with precision, and we can describe how it changes the future of the cosmos, but its underlying nature remains one of the genuine open problems in all of physics. It behaves like a property of empty space itself, a faint outward pressure woven into the vacuum, present everywhere and growing in total influence as the volume of space grows. Whatever it is, it now dominates the universe, outweighing all the matter and all the radiation combined, and it has taken the reins of cosmic history. The size and the fate of the observable universe are, from here on, written mostly by this thing we cannot yet name, and the strange double motion of a swelling view and a shrinking reach is its signature. In the next part, we are going to face that contraction directly, because it is where the wonder of this story turns, quietly, into something closer to loss. We are going to meet the cosmic event horizon, the boundary of everything we could ever reach, and we are going to discover that the overwhelming majority of the galaxies we can see tonight are already beyond it, already lost to us in every sense except sight. The phrase we set aside earlier, to see is not to touch, is about to stop being a technicality. It is about to become the most important thing in the sky. The light arriving in your eyes tonight from the most distant galaxies left them when the universe was young, and in the time it crossed to you, those galaxies were carried so far that you are looking at something you have already lost. Let us go and understand what that means. Part 9. The light that has already left us. There are two horizons around us, and we have only been honest about one of them. The first is the one we have spent the whole night exploring, the edge of what we can see, the boundary out at 46 billion light-years, from which ancient light is still arriving. But there is a second horizon, closer in and far more final, and it governs not what we can see, but what we can ever reach. It is called the cosmic event horizon, and it marks the limit beyond which any signal we send today, travelling at the speed of light, will never arrive, no matter how long the universe lasts. It sits at roughly 16 billion light-years, and almost everything we can see lies beyond it. Let that arrangement sink in, because it is the strange geometry at the centre of this story. The edge of sight is at 46 billion light-years. The edge of reach is at about 16. Between those two numbers lies an enormous shell of the universe that we can see perfectly well, galaxy after galaxy, shining in our telescopes, and yet to which we could never send so much as a single photon of reply. Their old light reaches us. Our new light will never reach them. They are visible and unreachable at once, and the volume of universe in that condition is most of what we can see. The overwhelming majority of the galaxies in the observable universe, by a wide margin, are already past the point of any possible contact. This is the meaning of the phrase we have been carrying since the middle of the night. To see is not to touch. We let it sit earlier as a curiosity, a wrinkle in the physics. Now it becomes something with weight. The light entering your eye tonight from the most distant galaxies left them when the cosmos was an infant, and in the billions of years that light spent crossing to you, the accelerating expansion of space carried those galaxies so far, so fast, that no message you could ever send would catch them. You are not seeing those galaxies as they are. You are receiving a portrait of their youth, a letter from a sender who has already passed beyond any address you could ever write to. To look up at the deepest sky is to read mail from the permanently unreachable. There is a particular grief in this that is worth naming gently, because it is unlike ordinary loss. Nothing has been destroyed. Those galaxies are still there, presumably still turning, still forming stars, still as real as our own. We have not watched them die. We have simply been separated from them by a swelling of space that no speed can overcome, and the separation is silent and bloodless and complete. They have crossed the event horizon the way a ship crosses the curve of the earth and slips out of sight of shore, except that this horizon, once crossed, can never be recrossed. The galaxies we see beyond the event horizon are like faces in a photograph of a crowd long since dispersed. The image is sharp, the connection is gone. The numbers attached to this loss are stark enough to be worth stating plainly. Of all the galaxies we can presently see, the overwhelming majority, by some careful estimates well over 90%, are already beyond the event horizon, already past the point where any signal we sent could ever reach them. We did not lose them gradually over a long human history of looking. They were, for the most part, already unreachable before we ever built a telescope capable of seeing them. The sky has always been, since the moment we first understood what we were looking at, mostly a gallery of the already lost. Only a relatively small core of nearer galaxies remains within the reachable boundary, and even that core is shrinking as the acceleration continues. There is a particular vertigo in turning this on a specific point of light. Choose one of the faint smudges in the deepest image ever taken, a galaxy so distant its light left when the universe was a small fraction of its current age. That galaxy is real. It is, presumably, still there, a swirl of hundreds of billions of stars, with its own worlds, and perhaps its own watchers, looking back across the same impossible gulf. You can see it, you can measure it, study it, learn its shape and its age, and the chemistry of its light. And you can never, by any means physics permits, send it a single bit of information, nor receive anything from it newer than the ancient light already in your eye. It is as present to your instruments as it is absent to any possible touch. To look at it is to hold, at once, perfect visibility and perfect separation, and the mind struggles to keep both of those truths in view together, because nothing in ordinary life ever asks it to. Dark energy is the agent of this separation, and it works without drama, without any visible event, simply by making the expansion accelerate. As the expansion speeds up, the recession of distant galaxies speeds up with it, and one by one they cross the threshold where their recession outpaces any signal we could send. Every day, a few more galaxies that were, in principle, still reachable yesterday slip across the event horizon and become unreachable forever. The reachable universe is not stable. It is contracting, galaxy by galaxy, as the accelerating expansion carries the cosmos out of our grasp. And there is nothing to be done about it, because it is not a thing moving away that we might chase. It is the space itself, lengthening faster than anything can cross. So we arrive at the true shape of the title, and it is a double truth that pulls in two directions at once. The observable universe keeps getting larger. The present distance to its edge climbs, swept outward by expansion at several times the speed of light, and new shells of ancient light keep arriving to fill it. That part is real, and we have earned it honestly. But at the very same time, the reachable universe keeps getting smaller, draining away across the event horizon as dark energy accelerates the cosmos out of contact. The thing we can see is swelling, The thing we can touch is shrinking. And the same expansion of space is the cause of both, growing what we can observe while stealing what we could ever reach. It would be easy to let this curdle into despair, and we are not going to do that because the physics does not actually point there. The right response to this is not dread, but a kind of clear-eyed wonder and gratitude for the position we happen to occupy. We live at a moment when the sky is still full, when the light of countless unreachable galaxies still pours into our telescopes and tells us truthfully that the universe is immense and crowded and old. We can still read the whole history of cosmic structure written in arriving light. That is not nothing. That is, in fact, a privilege bounded by time, a window that is open now and will not always be. The galaxies beyond reach are still galaxies we can study, photograph, and understand, and the understanding is real even when the contact is impossible. There is also something almost clarifying in learning that sight and reach are different things, because it sharpens what observation actually is. To observe the universe has never been to possess it. It has always been to receive its light, to read the messages it sends, to reconstruct from those messages a picture of something we are not part of and cannot alter. The event horizon does not change the nature of that act. It only makes explicit what was always true, that the cosmos is mostly a place we look at rather than a place we move through, and that the looking is its own form of contact, the only form most of the universe will ever permit. But the contraction of the reachable universe is not the end of the story, because it raises a harder question about the future of the sight itself. If dark energy keeps accelerating the expansion, and galaxies keep crossing beyond reach, what happens to the view? Does the sky stay full forever, a permanent gallery of unreachable but visible galaxies? Or does the same acceleration that stole our reach eventually come for our sight as well, stretching the light of those distant galaxies until even seeing them becomes impossible? In the next part, we are going to follow that question all the way to its end, far into the future, to a time when the sky has emptied, and we are going to stand beside an astronomer who looks up into that emptiness and draws an honest, careful, and completely wrong conclusion about the size of everything. Part 10. The Sky That Empties. Let us go forward in time, far past any span that human words were built to hold, and see where the accelerating expansion leads. The galaxies beyond the event horizon are unreachable now, but they are still visible, still pouring their ancient light into our telescopes. That visibility, it turns out, is also temporary. The same dark energy that carried those galaxies beyond our reach is, slowly, stretching their light toward the point where it can no longer be seen at all. The recession that took our touch will, given enough time, take our sight as well. The mechanism is the redshift we have known all night, run forward without end. As a galaxy recedes faster and faster, its light is stretched further and further, dimmed and reddened, and drawn out toward wavelengths too long and too faint to detect. A galaxy does not wink out suddenly. It fades, its light sliding down the spectrum, growing dimmer and longer and colder, until it crosses from merely faint into genuinely undetectable. One by one, over immense stretches of time, the galaxies outside our own gravitationally bound neighborhood will fade in exactly this way, their light stretched past the reach of any instrument, until the space between the local stars holds nothing visible at all. Our own neighborhood is spared, and that exception matters. The Milky Way and Andromeda and the few dozen smaller galaxies bound to them by gravity are held together far too tightly for the expansion to pull apart. Gravity wins locally, expansion only wins in the unbound gulfs between such groups. So our local group will survive, and in fact, it will draw closer together. Andromeda is already falling toward us, and in a few billion years, the two great spirals will collide and merge into a single elliptical galaxy, sometimes nicknamed Andromeda, with the smaller members eventually folding in as well. That merged island of stars will remain, gravitationally sealed, a permanent home. But beyond it, the rest of the universe will have receded into darkness. Now stand, in your mind, on a world in that distant future, perhaps 100 billion years from now, orbiting a dim and patient star deep inside the merged remnant of our galaxy and Andromeda. Beside you is an astronomer, as curious and careful as any who has ever lived, equipped with instruments finer than anything we possess. They point those instruments at the blackness between the local stars, the way our astronomers point theirs at the dark between galaxies, and they search for what lies beyond their island of stars. They find nothing, no other galaxies, no faint smudges of distant light, no background glow left over from any beginning. The microwave background itself, the oldest light, has by then been stretched so far that it too has faded past all detection. The astronomer's sky ends at the edge of their own galaxy, and beyond it there is only black, uniform, empty space without a single external landmark. What conclusion will that astronomer draw? They will draw the only honest one their evidence allows. They will conclude that the universe is a single island of stars surrounded by infinite empty darkness, that their galaxy is all there is, that the cosmos is small and local and alone. And they will be wrong, profoundly and irreparably wrong, not because they reasoned badly, but because the evidence that would have corrected them has been carried beyond their horizon and erased from their sky. The truth that their galaxy is one mote among hundreds of billions in a universe 93 billion light-years across and possibly infinite will be written nowhere they can read it. The expansion will have hidden the universe from the very minds most eager to understand it. This is not idle speculation, but a conclusion that working cosmologists have stated plainly. If intelligent observers arise in that far future, and do their science as carefully as we do ours, they will have no way to discover the expansion of the universe at all, because there will be no distant galaxies whose redshift could reveal it. They will have no way to find the leftover glow of the beginning, because it will have faded past detection. The entire body of evidence that taught us the universe is expanding, ancient, and immense will have been carried out of reach. Their cosmology, however rigorous, will describe a single static island of stars in an eternal void, and there will be no observation available to them that could prove it wrong. The truth will not have been forgotten. It will have been deleted from the sky. The thought has a sharp edge when you turn it back on ourselves. If the future can lose access to true facts about the universe simply because the evidence recedes beyond reach, then we have to ask what evidence has already receded beyond our own reach, what truths about the cosmos were once readable and are now gone, erased, before we ever arrived to look. We tend to assume that the universe we can study is the universe entire, that what we cannot see was never there to be seen. The far future warns us that this assumption is exactly the mistake the lonely future astronomer will make, and that we may be making a quieter version of it right now. We are reading the sky during a chapter when much of it is still legible, but not all of it, and never all of it, and the humility that follows from that is part of what it means to understand our place honestly. This is the moment to feel the strange privilege of where we stand, because it is the emotional center of everything we have built tonight. We did not arrive too early or too late. We arrived in the one cosmic era when the evidence is still in the sky. The light of countless galaxies still reaches us. The oldest light still glows faintly in our radio dishes. The history of the universe is still legible overhead for anyone who learns to read it. Future minds will be born under an emptied sky and will reason their way, carefully and wrongly, to a tiny and lonely cosmos. The richness of our night is not permanent scenery. It is a window, open now and slowly closing, and we are among the ones who get to look through it while it is still clear. There is a responsibility folded into that privilege, though it is a quiet one. The knowledge we gather now, about the true scale of the universe, about the galaxies that will one day vanish from view, is knowledge that could, in principle, be preserved and passed forward across the eons to those future observers, a message from an era that could still see to an era that cannot. Whether any mind will be there to receive it is unknown. But the very fact that we can presently see what they will not means we are, in a sense, the universe's witnesses during the only chapter when the whole story is still visible on its face. To be alive now, with telescopes pointed outward, is to stand in the lit room while the windows are still clear, and to know that they will not always be. So the observable universe keeps getting larger, and yet its future is a long fading. The boundary sweeps outward even now, but the light inside it is, in the immense future, draining away into undetectable redshift, until an emptied sky tells a lie to whoever is left to look. Growth and loss are braided together in the same expansion, and we happen to live at the hinge, when the sky is fullest and the truth is most readable. The horizon still breathes outward, but it breathes over a cosmos that is, in the longest view, emptying. We have nearly closed the circle, but one enormous question still stands open, and it is the one the whole night has been quietly circling. We have spoken endlessly about the observable universe, the part whose light can reach us. We have said almost nothing about how much lies beyond it. If the sphere we can see is 46 billion light-years in radius, and possibly only a sliver of the whole, then how big is the whole? Is there a far wall somewhere out past our horizon, or does the universe simply continue without end? In the next part, we are going to step as far as reason can carry us, beyond the edge of the observable, and confront the possibility that the part we can see is not most of the universe, and not even a meaningful fraction of it, but a single grain in something without any edge at all. Part 11. Beyond the edge of the map. Everything we have measured tonight concerns the observable universe, the sphere whose light has had time to reach us. But that sphere is defined entirely by us, by our location and our moment in time, and there is no reason to think the universe itself stops at our horizon any more than the ocean stops at the horizon a sailor sees. The natural question, then, is how much lies beyond? And the honest answer is that we do not know the whole size, that we may never know it, and that the universe might have no edge at all. What we can do is gather the clues that survive at the boundary of the observable, and follow them as far as careful reasoning allows. The first and most powerful clue is the shape of space itself. The geometry of the universe can, in principle, be curved, like the surface of a sphere that closes back on itself, or flat, like an endless sheet, and we can measure which it is by studying the patterns in the oldest light. Those measurements have come back again and again with the same answer. Space is flat, as far as we can tell, flat to within a tiny margin of error. The curvature, if there is any at all, is so slight that it is consistent with zero, and a universe that is genuinely flat and connected in the simplest way is not finite. It is infinite, extending without limit in every direction, with no far wall anywhere. Now, measurements have error bars, and a nearly flat universe could still be very gently curved, and therefore finite but enormous. So cosmologists have asked what the measured flatness implies as a minimum. Even taking the cautious view, the lack of any detectable curvature means the whole universe must be at least hundreds of times larger across than the part we can observe. One careful analysis put the lower bound at around 250 times the radius of the observable universe, and that is only the floor, the smallest the whole thing could be, while still looking as flat as it does. Some estimates, rooted in the theory of cosmic inflation, the brief and violent expansion thought to have stretched the early universe, push the true size to at least a trillion times larger than what we can see, and many cosmologists are entirely comfortable with the possibility that it is simply infinite. Sit with the proportions for a moment. because they are humbling in a way that is hard to fully take in. The observable universe, 93 billion light-years across, the immense sphere we have spent all night measuring and marveling at, may be to the whole universe as a single grain of sand is to a desert, or less. Everything we can ever see, every galaxy in every deep telescope image, the entire history of cosmic structure, written in arriving light, might be a vanishingly small sample of a cosmos so much larger that the word larger loses its grip. We have not been measuring the universe. We have been measuring the part of the universe that happens to be close enough in time and light to send us a signal. The rest is simply beyond. If the universe really is infinite, a genuinely strange consequence follows, one that sounds like fantasy but falls straight out of the mathematics. In an infinite space filled with matter arranged according to the statistics we observe, every possible arrangement of particles must occur somewhere, and not just once, but infinitely often. That includes the arrangement that is you, in this room, listening to these words. Somewhere out in that endlessness, by one estimate impossibly far away, far beyond any horizon, there would be a region indistinguishable from the one you occupy, with a version of you in it. This is not mysticism. It is the cold arithmetic of infinity and probability, and while it lives well beyond anything we could ever test, it is what an infinite universe with our physics would imply. There are grander possibilities still, layered out past the edge of testability. The theory of inflation, in many of its forms, does not produce a single universe, but an endless froth of them, bubble after bubble of space inflating into existence, each one a self-contained cosmos, with perhaps its own properties, the whole ensemble, sometimes called a multiverse. Our entire observable universe, on this view, would be one small region within one bubble among an unending profusion of bubbles. It helps to organize these layers of possibility because they are often jumbled together into a single vague notion of other worlds. The simplest layer is just more of the same universe beyond our horizon, ordinary space continuing on past the edge of what we can see, filled with galaxies obeying the same physics, differing from our visible patch only in the particular arrangement of their contents. If the universe is infinite, this layer alone already contains the distant repetitions we just described. A further layer imagines entire separate regions, the bubbles of eternal inflation, each a self-contained cosmos, perhaps with different physical constants, born from the same restless, inflating background. And there are layers more abstract still, which propose that every possibility allowed by the mathematics is somewhere realized. The layers differ enormously in how speculative they are, and careful thinkers are at pains to distinguish the nearly certain from the frankly conjectural. What is striking is how little of this we are forced to invent, and how much falls out of measurements we already trust. We did not set out to find a possibly infinite universe. We measured the geometry of space, found it flat, and infinity arrived as the simplest reading of that flatness. We did not set out to populate the cosmos with distant copies of ourselves. We took infinity and our observed matter statistics seriously, and the copies followed as cold arithmetic. The boldest of these ideas are extrapolations, yes, but they are extrapolations of a framework that has earned extraordinary trust inside our horizon, and that is why serious scientists entertain them rather than dismissing them out of hand. The honest position is neither belief nor mockery, but a careful holding open of possibilities that the evidence permits and that it forbids us from ever closing. These ideas are serious extrapolations of equations that work beautifully inside our horizon, carried out into the one place we can never check. They may be true, we may never be able to know whether they are true. And that combination of being possibly real and permanently unverifiable is itself one of the defining features of everything that lies beyond the observable edge. What ties all of these speculations together is a single discipline we have to keep, which is the difference between the universe and the observable universe. The observable universe has a size, a measured and meaningful size, 46 billion light-years to the edge, and that size is real and growing. The universe, the whole thing, has a size we cannot measure and may not even be finite. When you hear that the universe is 93 billion light-years across, the honest footnote is always the same. That is the part we can see. The part we cannot see dwarfs it by an unknown and possibly infinite factor, and no instrument we could ever build from inside our horizon will close that gap, because the information simply cannot reach us. This is the final humbling, and it sets up the last turn of the whole story. We began with a person doing confident arithmetic, multiplying the age of the universe by the speed of light, and believing they had found the edge of everything. We are ending with the recognition that there may be no edge at all, that the universe we can measure is a horizon-bound bubble, adrift in something immeasurably larger, and that our position at the center of our own sphere is shared by every observer everywhere, each one equally central and equally bounded. In the final part, we are going to gather all of this into a single image, the image of standing at the center of a sphere that has no center, and we are going to ask what it actually means to know the size of a universe from a place inside it that can never see the whole. Part 12. The center that has no center. We began the night with a simple sum and a comfortable picture, a universe 13.8 billion years old, an edge 13.8 billion light-years away, a tidy bubble with a wall at the back. We are ending somewhere almost unrecognizable from that starting point, holding a universe at least 93 billion light-years across, in the part we can see, growing larger by the year, draining beyond our reach at the same time, and possibly without any edge at all. The single quiet correction that carried us all this way was the recognition that space is not a fixed stage, but a thing that stretches, and almost everything strange about the scale of the cosmos unfolds from that one fact. Let us gather what we have learned into one steady picture before we let it go. The observable universe is enormous beyond its age, because space expanded while light crossed it, so the matter we see is now far farther away than the light's journey alone would suggest. It keeps getting larger for two reasons: the patient arrival of ever-older light revealing new shells of sky, and the expansion of space itself sweeping the boundary outward faster than light. Its edge is not a wall but a horizon, the oldest light marking the moment the universe turned clear, with more universe hidden behind it. And threaded through all of this is the quiet reversal, that the same expansion, enlarging what we can see, is carrying most of it permanently beyond what we can ever reach. Hold now the image we have been building toward since the middle of the night. You are sitting at the exact center of your observable universe. 46 billion light-years of it surround you in every direction, a near-perfect sphere with you precisely in the middle. And the strange thing, the thing that turns this from a fact into something close to a revelation, is that everyone is. A being on a world, in one of those faint and distant galaxies, looks out and finds their own sphere, the same size, equally centered on themselves, with us near its dim and ancient edge. Every observer who has ever lived, on every world that has ever held a curious mind, sits at the center of their own observable universe. All of those centers are real, none of them is the center. You are standing at the center of a sphere that has no center, and that sentence is no longer a riddle. It is simply what an expanding universe with no middle produces for everyone inside it. This is why the edge of the observable universe was never a place. It is a relationship between you and the cosmos, set by where you stand and when you happen to live, and the unbreakable speed of the light that carries the news. Move to another galaxy, and your horizon moves with you, a new sphere centered on the new home. Wait 100 years, and the horizon shifts as more light arrives. The boundary belongs to the observer, the way the horizon at sea belongs to the sailor and not to the ocean. There is no painted line out there in the dark. There is only the limit of how far the light has been able to come, and that limit is yours alone, shared in form, but not in location with every other watcher in the cosmos. We also have to carry the gentler grief honestly, because it is part of the truth and not separate from the wonder. To see is not to touch. The light reaching your eyes tonight, from the most distant galaxies, is a letter from a youth that is, for any purpose of contact, already gone, carried beyond reply by the swelling of space. Most of what we can see, we have already lost in every sense but sight. And in the long future, even the sight will fade, the galaxies stretching into darkness, until an emptied sky misleads whoever is left to look. We live in the seeing time, the one era when the evidence is still overhead and legible, and that is not a small thing to be handed. It is the rarest kind of luck, to exist while the windows are still clear. Think about what had to line up for you to be the one reading this light. The universe had to be old enough for stars to have formed and forged the atoms you are made of, old enough for galaxies to have assembled, and for a quiet world to have cooled and steadied long enough for curious minds to appear. But it also had to be young enough that the accelerating expansion had not yet swept the distant galaxies into darkness, young enough that the oldest light still glowed in the sky, and the history of the cosmos was still written where it could be read. That window between a universe too young to have made us and a universe too old to still show itself is the window we were born into. It is not infinitely wide. It will close. And we are inside it now, with instruments pointed outward, during the chapter when the whole story is still visible on the universe's face. That is a strange and specific gift, and the right response to it is not anxiety about the ending, but attention to the present. The light is still arriving. The galaxies beyond reach are still pouring their ancient images into our telescopes, still teaching us, truthfully, that the cosmos is immense and crowded and old. Every clear night, the evidence is overhead, free for anyone who learns to look, and the looking itself is a kind of participation in the universe's brief moment of self-knowledge. We did not choose to be born in the seeing time. We simply were, and the only fitting answer to that luck is to use it, to read as much of the sky as we can, while the sky still tells the truth. So what does it actually mean to know the size of the universe from a place inside it that can never see the whole? Perhaps it means exactly what we have done tonight, which is to read the light we are given as carefully as we can, to follow the clues at the edge of the observable, as far as reason allows, and to hold with open hands the enormous part that is hidden from us. We can say with real confidence how big the part we can see is, and that it is growing, and why. We can say that the whole is vastly larger, at least hundreds of times across, perhaps infinite, and that we will likely never measure it. Knowing the size of the universe turns out to be inseparable from knowing the limits of our own position within it, and there may be no deeper kind of knowledge than that, the kind that tells you honestly where the map ends. The observable universe keeps getting larger, then, in the way that matters to the question we started with. The boundary sweeps outward, the ancient light keeps arriving, the sphere of what we can see swells year by year. And yet, it is bounded, and it is bounded by us, by our moment and our location and the patience of light. The number 46 billion light-years is not the size of everything. It is the size of everything we are presently allowed to see, a horizon cast by a watcher who happens to be alive at this hinge of cosmic time, when the sky is fullest and the truth is most readable and the long fade has not yet begun. When you next step outside and look up, you will be looking at the inside surface of your own observable universe, a sphere of light 46 billion years deep in every direction, still growing, still arriving, with you exactly at its center and no center anywhere to be found. The light landing in your eyes left its sources across the entire history of the cosmos, the nearest from minutes ago, the oldest from before there were stars at all, And all of it is still coming, still finishing journeys begun billions of years ago, still widening the only edge any of us will ever know. The universe is far larger than its age should allow. It is quietly getting larger still, and the most honest thing we can say about its true and total size is the one thing that keeps the wonder alive. We do not know. We are inside it, looking out, reading the light while the light still reaches us. And that may be the most remarkable thing a small mind on a small world is ever given to do.